It is important to note that much of the material in this video consists of educated guesses that may not always be accurate. This is consistent with the fundamental nature of science, which thrives on hypothesis and uncertainty. Many people have heard that our universe is about 13.8 billion years old, and that it came into existence as a result of the Big Bang. But the question here is, what do we call the universe, and what does a beginning mean? When confronted with the claim that the universe came from nothing, it would be more accurate to say that it came from something beyond our understanding. Theoretical physicist Matt Strassler, in his article, The Hot Big Bang, emphasizes that discussions about the age of the universe refer specifically to the period from the beginning of the Big Bang to the present. But that doesn't mean there was nothing before the Big Bang. And absolutely, the same applies not only to time, but also to space itself. According to existing theories, at the moment of the Big Bang, the universe was centered at an extremely small point, with a finite size smaller than an atom. It is important to realize that these considerations apply only to the observable segment of the universe. This does not negate the possibility that the universe was infinite at the time of the Big Bang. Although the evidence suggests a much greater density, the concept of infinity remains a mysterious aspect that is best approached with caution. Soon, all of what has been said will become a little clearer to you. In August 1881, Nietzsche was walking along Lake Silvaplana near the village of Surley in Switzerland and stopped to rest right next to this pyramidal rock. At that very moment, the philosopher was pierced by a thunderbolt of insight. As he later put it in a letter to his friend and assistant Peter Gast, a thought arose on my horizon, the like of which I had not yet known. This moment was so important that it was immortalized by this plaque on the rock. The quote on it literally reads, "I stopped at a powerful pyramidal block near Surley." It was then that the thought occurred to me. Nietzsche realized that the idea that struck him must be the most important idea in his philosophical teachings, but at the same time, the most terrible, so terrible that he was very reluctant to talk about it at all. Those who knew Friedrich Nietzsche, particularly his close friend Franz Overbeck and his unrequited love, Andreas Salome, later said that Nietzsche spoke of this idea in whispers and implied that it was some unheard-of discovery. Nietzsche believed that this idea would not be overwhelming if properly understood, that it was meant for those he called superhuman. The term superhuman here does not refer to a comic book character, but is Nietzsche's conception of a being who should surpass modern humans in psychological qualities to the extent that humans surpass apes. And speaking of might, it is more about psychological qualities. We'll get to the very thought that Nietzsche illuminated, but first, there's a lot to explain to you. First of all, let me share one of the most intriguing cosmological anomalies. Normally, objects appear smaller as they get farther away from us, similar to the way humans look like ants from a bird's eye view. This phenomenon is true, even in close cosmic proximity, exemplified by the fact that the sun is 400 times larger than the moon. However, during a total solar eclipse, the moon almost completely covers the sun because it is 400 times closer to us than our luminary. This pattern of size variation with distance extends over billions of light years. Galaxies, for example, appear smaller the farther away they are, as you might expect. Yet, at a certain point about 14 billion light-years away, there is a dramatic change. Surprisingly, the farther away an object is at this distance, the larger it appears. The explanation for this unexpected phenomenon is simple, yet sad. It may seem implausible at first, but observing any star or galaxy in the night sky means that you are currently under the gravitational influence of that celestial object. Even if the object is far away from you, its gravitational field reaches you at the speed of light. For example, when you see the sun, you perceive it as it was 8 minutes and 20 seconds ago. The gravitational pull of our entire planet is not directed to the current position of the sun, but to where it was in the past. What makes gravity unique is its constancy, as it weakens with distance, but never decreases to zero. I'm not sure the gravitational effects of very distant objects are even remotely possible to register, unless it's a merger of two black holes, for example. Remarkably, gravitational force can make all massive objects in our universe eventually collapse. It is impossible to get far enough away from an object to completely escape its gravitational influence. Despite this, our universe is not shrinking, rather the opposite. The universe is expanding, and intriguingly, this expansion is accelerating. The cause of this phenomenon remains unknown. Physicists, lacking a clear understanding of the force propelling the universe's expansion, commonly attribute any hypothetical phenomenon driving this acceleration to dark energy. Although discussions on dark energy may seem repetitive in numerous space-related videos, it stands out as one of the most perplexing and enigmatic phenomena in the world of physics. Katie Mack, an assistant professor of physics at North Carolina State University, writes, "If you ask my colleagues, they will tell you that they are eager to understand the nature of dark energy because it can tell us a lot about fundamental physics and our cosmological model. But I know that what really drives them is fear." So, the expansion of the universe. Rewinding time back 13.8 billion years, that is, somewhere near the very conventional beginning, we will find a paradoxical moment in which for some reason we do not understand the expansion of the universe just suddenly accelerated. The region destined to become our observable universe expanded by over 100 trillion times. This expansion occurred at a rate surpassing the speed of light, as there is no constraint on the rate of space expansion itself. While the magnitude of these numbers may be challenging to comprehend, theoretical physicist Matt Strassler, introduced earlier, provides insights for clarity. How insane is this rate of expansion? A patch of the universe no larger than your computer screen expanded to the size of the observable patch of the universe, or larger in less than the time it takes for a quark to cross from one side of proton to the other. But then this monstrous expansion again inexplicably slowed down. And so this frenzy that occurred has a name: the cosmic inflation hypothesis. We don't know for sure if that expansion in the beginning is related to the expansion that we're seeing now. It is important to note that there is no reason to rule out the possibility of cosmic inflation happening again, perhaps even at this moment. As you watch this video, such an event could happen too quickly for us to perceive it. The consequences of such a recurrence could be dire, with the potential for catastrophic consequences exceeding the mere extinction of humanity. You may wonder, what could be worse for humanity than its total annihilation? Let's look into this. As you probably know, the expansion of the universe does not originate from any particular point, but occurs simultaneously at all points. And so the farther away an object is, the faster it moves away from us. To illustrate this, imagine the stretching of a child's toy spring, where each coil becomes a finger's width away from its neighbor. At the same time, the two coils at opposite ends are more than a meter apart. Apply this concept to galaxies in the universe. Thanks to this mechanism, distant galaxies can move away from us at a speed equal to or greater than the speed of light. It is important to note that there is no limit on the rate of expansion of space. Consequently, at a certain distance from us, objects can appear larger the farther away they are. This phenomenon occurs because we can observe objects moving away from us at superluminal speeds, driven by the expansion of space. When these objects were emitting their light, they were much closer and took up more space in the sky, given the denser nature of the universe at the time. Although these objects are now much farther away, the light they emitted traveled through space, and thanks to a period of slow expansion, their image has finally reached us. It's a ghostly image of a much closer and older object. Therefore, the further back in time we look, the more compressed the universe we observe. Consequently, a galaxy that is now at a greater distance than another galaxy may have been closer at the time the light was emitted. Hence, the paradox of perception, illustrated by a real-life example with GNZ 11, one of the most distant galaxies ever observed. This ghostly image we see has been traveling to us for about 13.5 billion years. While it may appear to be closer, we are actually observing the universe as it existed just 400 million years after the Big Bang, when it was much more compact. Meanwhile, due to the expansion of the universe, GNZ 11 is about 32 billion light-years away from us, and actually appears to be twice as large as a galaxy of the same size that is twice as close. This paradox arises because we observe the past universe because of the time it takes for light to reach us. The conventional understanding of a light year as the distance that light travels in a year might lead one to think that, given the age of the universe at 13.8 billion years since the Big Bang, the maximum observed distance should be 13.8 billion light years. However, the influence of dark energy allows us to see much farther. Currently, our observed limit is a sphere with a radius of 46 billion light-years, expanding due to the ongoing expansion of space. Future calculations indicate that the limit of visibility will be about 33% larger than the current limit, reaching 61 billion light-years away. Eventually, the image of the GNZ 11 galaxy will gradually fade and disappear forever. This inevitability is due to the realization that the light currently emitted by this galaxy will never reach us again unless there is a slowdown in the expansion of the universe. GNZ 11 is currently moving away from us at a staggering 687,000 kilometers per second, twice the speed of light. And that's sad. But what's even sadder is that it doesn't end with GNZ 11. Think about it. 96.7% of galaxies observed today have already disappeared this way. Amazingly, 98.6% of the galaxies that will ever be within our observational reach have already disappeared. In other words, we have a total of 4,700,000,000,000 galaxies to see in the future, and 4,634,000,000,000 of them are already forever out of our reach, even if we could reach them at the speed of light. Currently, only about 66 billion galaxies remain accessible to us. I emphasize, today, because this problem is only going to get worse as time goes on. Currently, if we assume that each of the 66 billion galaxies contains the same number of stars as the Milky Way, about 400 billion stars, then about 60,000 stars disappear from our field of view every second. That means that in the time we watch this video alone, about 50 million stars will disappear. Although we will continue to perceive their past light for billions of years, any new light generated by these stars, from this point forward, will forever elude us. These celestial objects no longer have a causal relationship with us. Regardless of our actions, from this point forward, we can never affect them, nor can they affect us. Any information about these places is now fundamentally inaccessible to us. Even with advanced technology, more than 98% of all galaxies intended for our observation are no longer accessible. If the force of expanding space can never overcome the gravitational force within galaxies, then a gradual descent into darkness awaits each galaxy or localized group of galaxies. These cosmic entities will remain isolated. Stars will shrink, particles will decay, and black holes will be dissipated by Hawking radiation. Eventually, the universe will become a desolate space, devoid of celestial activity. Stars will burn out, particles will decay, and black holes will dissolve into nothingness. Only dark energy will persist, forever driving exponential expansion. It should be noted here that dark energy is sort of the opposite of gravity. That is, the more filled the space is, the stronger the gravitational force, and the more empty space is, the stronger dark energy is. Despite its counterintuitive nature, the density of dark energy per square meter does not decrease with the expansion of space. That is, do you understand what is happening? As the expansion of the universe accelerates, there will be more and more empty space, which in turn will lead to the acceleration of the expansion process, which will lead to more empty space, and so on ad infinitum. In such a scenario, events in one place in the universe lose the ability to affect events elsewhere. Eventually, the universe becomes a vast void, sustained only by the dark energy that drives its limitless, exponential expansion. Such a state is called de Sitter space, and physicists draw parallels between its evolution and the early cosmos at the inflation stage. Unlike inflation stage, however, this expansion is predicted to continue indefinitely. The question arises, can this infinite expansion be considered the end of the universe? The answer depends on our understanding of what the universe is and our definition of its end. Notably, the concept of time itself remains one of the unsolved mysteries of physics. No one knows why it should flow in a particular direction. The question arises, are the particles moving into the future or into the past? The perplexing reality is that the answer remains elusive, regardless of how the animation depicting the motion of these particles is reproduced. The governing laws stubbornly maintain their symmetry in time. At the microscopic level, physical processes are assumed to be either completely or mostly symmetric in time. If the direction of time were reversed, changing the direction of time in the equations would have no effect on the outcome. Now, let's shift our attention to another scenario. Is this paint separating from or mixing with water? Here, a clear distinction between past and future emerges at the macroscopic level, establishing an obvious direction of time. Entropy, a fundamental concept of physics, seems to be the only aspect of this field that draws attention to the direction of time. Why is it that your closet of stuff is in total chaos, again, sometime after you clean it out? Imagine your closet, and imagine every possible way to arrange things in it. Nicely, great. Now imagine all the ways you can arrange them in a way that isn't pretty. And because there are so many more ugly options, the likelihood that the system called a closet of stuff will gradually become more and more chaotic is greater than the likelihood that the system will continue to maintain some sort of orderly form. Because of the second law of thermodynamics, which states that in an isolated system, the total entropy cannot decrease. Your closet will sooner or later become a mess again. You may say, so I stacked things, and therefore lowered the entropy inside the closet. Did I violate the laws of physics? No, because a closet is not an isolated system, and you expended a lot of energy cleaning it. You were digesting food and releasing carbon dioxide. The air in the room was heated by the convention of sweat. In fact, the total entropy has increased even more, indicating the pervasive nature of disorder. An example of this phenomenon is the counterintuitive result of trying to cool a room by leaving the refrigerator door open. Instead of cooling, the room heats up. The desire to bring order to one part of the world inevitably produces disorder in another, usually in the form of heat. And of course, we don't know this for sure yet, but perhaps it is entropy that creates what we call time. Everything in the universe we observe, from galaxies and stars to humans, is a consequence of the initial, incredibly ordered state of the universe at the time of the Big Bang. The subsequent evolution from this ordered state to a disordered state is what we define as the passage of time, like stirring paint in water. And just as we couldn't tell which way time was flowing in the frames with the paint already fully mixed in the water, in the same way, in the universe, the concept of the arrow of time ceases to exist when it comes to maximum entropy. The perceptible passage of time in a constant direction indicates that the universe has not yet reached the equilibrium state to which the entropy law gravitates. Once the de Sitter state is reached, the universe will reach an entropy maximum, marking the point at which the total entropy can no longer increase. Which means that nothing else can happen, in the sense we're used to, because for something to happen, energy must move from one place to another. But alas, the paint in the water has completely stirred. Entropy, essentially synonymous with homogeneity, becomes predominant in this state of the universe. Given that the universe is expanding, not from any point but at all points simultaneously, when it reaches the stage of exponential expansion, it will be possible to outline a sphere around any point, beyond the boundary of which will be a forever hidden part of the cosmos. Just as the stars we talked about earlier are now forever hidden from us, and it has a name. The heat death of the universe. You ask, why should we care? Why is it worse than the death of mankind? By the time heat death happens, we'll have been gone so long that it won't matter. That's where we get to what I was talking about at the beginning of the video. Because there's one thing that makes all the difference. Ask yourself two questions. 1. What happens when you have an infinite amount of time? And 2. What happens when you have an infinite amount of space? The answer to both of these questions is everything. Literally, everything within the laws of physics. Can you suffocate because all the oxygen in a room gathers in one corner? Never. Entropy protects you from this situation because, as you remember, there are far more disordered states than ordered states, so no investigator would even think of such a version of your demise. But in fact, when we say the word never, we mean the word usually. Decreased disorder in the system is possible, is just extremely unlikely. People don't normally suffocate because all the oxygen is collected in one corner of a room. But conventionally, if you were sitting in that room for an infinite amount of time, it would happen with 100% probability. And a completely empty universe only appears empty at first glance, because even where there are no particles, there are still quantum fields that never behave completely quietly. Quantum fields do not maintain a constant value. Their value at any point in space is always jittering a little bit. The jitters are called quantum fluctuations, and they are nothing but consequences of Heisenberg's famous indeterminacy principle. And at the quantum level, or even at larger scales, if you're willing to wait long enough, really weird things happen from time to time, caused by unpredictable fluctuations that can shift some part of the system to a lower entropy, lower homogeneity state. So, even if we believe that the universe had a beginning and that it is not infinite in space, nevertheless, in an expanding universe, time and space become so plentiful that extremely unlikely events can and will occur with 100% probability. It is unlikely that an entire piano will spontaneously assemble in empty space. However, physicists such as Anthony Aguirre, Sean Carroll, and Matthew Johnson have calculated that given a huge period of time, trillions and trillions of times the age of the universe, it will manifest before our eyes. The lower the probability of an event, the longer the wait. However, in a scenario with infinite space, infinite time, or both together, any event, no matter how unlikely, will occur an infinite number of times. The implications arising from thinking about the heat-death hypothesis of the universe are deeply disturbing and can make one numb with horror. The thought that pierced Nietzsche, which we talked about at the beginning of the video, a few months after the Epiphany, Nietzsche would write a book called The Gay Science, where he very carefully touches on his idea at the very end, in the penultimate passage of the first edition of the book, which he would call the heaviest burden. It sounds like this. What if one day or night a demon crept into your most secluded solitude and said to you, the life you have lived and are living now, you will have to live again and innumerable times, and there will be nothing new in it. But every pain, every joy, every thought, every sigh, and everything unspeakably small and great in your life will be repeated in the same sequence. Even this spider and this moonlight between the trees, even this moment and myself. The eternal hourglass of existence will turn over and over again, and you are a grain of sand along with it. You throw yourself to the ground, gnashing your teeth and curse the demon who spoke like that. Or once you had an amazing moment in which you could answer him, you are God, and I have never heard anything more divine. If that thought takes hold of you, it will change who you are and maybe crush you. The question of whether you want to experience it again innumerable times will henceforth weigh heavily on all your actions. And how well would you have to treat yourself and life to long for this eternal affirmation and sealing more than anything else? The final section of the book was entitled The Birth of Tragedy, which would later become the preface to Nietzsche's seminal work, Thus Spoke Zarathustra, a book for everyone and no one in particular. At the heart of Thus Spoke Zarathustra is the concept of eternal return, which asserts that time repeats itself in an endless cycle, and that the same events will continue to happen exactly the same way, over and over again, throughout eternity. In developing this concept, Nietzsche probably proceeded from certain assumptions. One was that in an infinite universe with a fixed amount of matter, any possible combinations of that matter would eventually repeat themselves in the same way. Even if Nietzsche was far removed from today's cosmological theories, his conclusion may be correct. This conclusion finds support in the de Sitter equilibrium hypothesis of cosmologist Andreas Albrecht. In essence, this hypothesis suggests that the origin and ongoing processes of our universe can be explained by random fluctuations in a constantly expanding space dominated by dark energy. In this vast space, quantum processes periodically lead to a jump to a state of extremely low entropy, giving birth to a universe that then gradually returns to its typical state of high entropy, again resembling a de Sitter universe. This cycle resembles a scenario where oxygen concentrated in one corner eventually disperses evenly throughout the room, and everything repeats over and over in a circle. Of course, not every Big Bang event results in a universe identical to our own in every detail. However, that is the troubling consequence of infinity. With infinite time, it is inevitable that our universe will eventually repeat itself exactly, and we will be here, communicating with you again, and it will happen an infinite number of times, and also having an infinite de Sitter space. Big Bangs evolving exactly into our universes happen at every moment, an infinite number of times. This whole process is described by a model of the universe called eternal inflation. We are all so dismissive and easy to talk about eternity or infinity even for a second without really thinking about what is really behind these concepts. You may say, what do we care? No matter how many times the universe repeats itself, it won't be us. But this begs the question, what does it mean to be you? You often hear from people who consider themselves non-religious that life is one and that we live once. But isn't there more religiosity in that statement than the reverse? So, in other words, these people are saying that their consciousness is fundamentally impossible to recreate. A strong statement, because if you break it down into its premises, it turns out that consciousness is something detached from the material world. How long does it take for another Big Bang? There are some calculations that tell us that inflation will produce a new Big Bang in about 10 to the 10th to the 10th to the 56th degree of years. If an entire universe can emerge from a vacuum due to quantum fluctuations, it is much more likely that a single galaxy can do so, because it is less complex and requires less matter to create. And if you continue to follow this logic, it is more likely that a single solar system or a single planet, or even just today, this very moment, and all the other moments of your life. In fact, even more likely is the emergence of a separate thinking structure, such as a human brain, that contains all your memories and imagines that it lives in a vast and complex world, and is currently watching a YouTube video in which the author states hypotheses that are most likely unverifiable. You do not notice this illusion, because for you, as an observer, there is no space and time outside your consciousness. That is, you cannot be an observer of a dream without dreams. You fall asleep and immediately wake up in a new day. If you have a suspicion that this sounds like some kind of schizophasia, but in fact, more than one generation of scientists have been puzzling over such ideas. The notion of a brain spontaneously materializing in the void is called a Boltzmann brain. This concept regained significance in 2002, when some cosmologists expressed concern that in numerous theories of the universe, the human brain is much more likely to arise from random fluctuations than from the emergence of an entire universe where evolution subsequently leads to human development. This is primarily because the spontaneous emergence of an individual brain from fluctuations is much more likely. For example, while a new universe emerges every 10 to the power of 10 to the power of 10 to the power of 56 years, a Boltzmann brain emerges only once every 10 to the power of 10 to the power of 10 to the power of 50 years. Hence, statistically speaking, humans are most likely mistaken in their perception of the past, and are instead unfortunate Boltzmann brains, constantly arising in an empty universe doomed to almost instant annihilation. Of course, we don't know all the potential variants of self-conscious entities that the laws of physics allow, or that our universe can give rise to. A Boltzmann brain pales in comparison to the myriad possibilities that, according to the eternal inflation model, the universe could give rise to. Even if you are not a Boltzmann brain, such concepts remain fascinating, reflecting on the astronomical number of variables required for the emergence of the human mind. One cannot help but speculate that infinite time or space may be involved. The notion of fluctuation potential is in profound contradiction to our notions of the intelligent design of the cosmos. Sean Carroll, a prominent cosmologist, has called it cognitively unstable. It's not that it can't be reliable. Rather, if it were reliable, it would make any attempt to comprehend the universe futile, because nothing would make sense. Nietzsche is often called a nihilist philosopher, ostensibly for his apparent denial of life in his philosophy. If the concept of eternal return implies the insignificance of events, then the concept of the superhuman, as set forth in Thus Spoke Zarathustra, must serve as a kind of imperative to the human will to create meaning. The uncompromising idea of eternal return rejects any hope of an afterlife or any consolation. Yet Nietzsche argued that it is the superhuman who has the courage to say yes to such a world, abandoning all the false hopes that religion, science, and philosophy have hitherto offered. Unfortunately, Nietzsche himself was not superhuman and called himself a decadent. For Nietzsche, who had a tragic fate filled with pain and suffering, the idea of eternal return was devastating, paralyzing, and absolutely terrifying. In his notes, he wrote, "I do not want to start life over again. Where would I get the strength to bear it? Creating a Superman and looking up to him, hearing him say, yes to life. I have, alas, tried to say yes myself." Perhaps this is why Nietzsche refers directly to his deepest idea, only one passage from The Gay Science, in two passages from Thus Spoke Zarathustra, once in Exe Homo and once in The Will to Power, as if he dared not face the idea for long. 8 years after the Epiphany and the most fruitful period of his life, Nietzsche went mad. There are different versions of why it happened. However, no consensus has ever been reached, and some even suggest a psychogenic origin for Nietzsche's madness. Unfortunately, the philosopher's illness showed no signs of abating, and on August 25, 1900, Nietzsche died in a state of complete insanity. Fortunately for Nietzsche, all those who are not superhuman, the heat death of the universe is only one of 5 possible scenarios, described in Kathy Mack's book, The End of Everything, which served as the basis for this video. Moreover, not all scenarios involve the hypothetical possibility of eternal return. Kathy Mack, the author of the book, is an authority on theoretical astrophysics. Freeman Dyson, a theoretical physicist known to the general public for his article Time Without End, Physics and Biology, in an open universe, sharply criticized the physics community for neglecting the topic of the end of the universe. Implying a lack of serious work on the subject, he wrote, "The study of the distant future today seems as dubious an endeavor as the study of the distant past seemed 30 years ago. If the analysis of the distant future raises questions related to the ultimate meaning and purpose of life, let us investigate them boldly and without embarrassment. Given the information presented today, perhaps we should approach this issue with caution. However, it is important to remember that much of what is discussed in this video are educated guesses that may not be confirmed.